Thank you. I forgot. Anyway, so that's it. Thank you. So you have here an x and an x. So when you divide, you have here 1. If you multiply this 1 to x minus 1, so this would be x minus 1. And of course, you need to subtract. When you subtract, this would be a 2. So it follows that x plus 1 divided by x minus 1 is actually integral of dx for this one, and this is a remainder. So you will have plus 2 over this particular divisor, x minus 1. So you need to integrate 2 dx over x minus 1 because this 2 is a remainder. If you integrate this part, this will be an x. If you integrate this part, this will simply be a u for an x minus 1 and a du, which is dx. So you already have it here. So these two, you write in here outside. So automatically, you will have here a 2 ln of the u, which is the one you see here in the denominator, x minus 1. Okay, plus c. So the original integral of x plus 1 over x minus 1 dx will have this as the answer, because you have to resort to long division, knowing that the degree of your numerator and your denominator are equal. If the numerator degree is higher than the denominator, you can divide by distribution, or you can divide also using this long method. Okay? Now we will go back to our slide. Okay? So this is it. So x plus 2 ln of x minus 1 plus c. Oh, wait. Let me check if I placed an x on the first part. Okay, so it's x plus 2 ln of x minus 1 plus c. Okay? Now going back to our slide. Okay, so that's it. Now we go to the next example. Now you have x plus 3 and x squared plus 6x plus 5. This time, the degree of the denominator is higher than the numerator. So there's no need for you to divide. So you just check whether it's possible. Whether it's possible. If it's not possible, there are other things, techniques that you can employ later on. So if your u, for example, is x squared plus 6x plus 5, if you get the derivative of this, that would be 2x plus 6. 2x plus 6, which if you factor out the 2, that would be 2 times the quantity x plus 3 dx. Good that you already have x plus 3 in the numerator. So all you have to do is, since you need a 2 here in the numerator, you need to multiply the original integral by 2 over 2. Set aside the 1/2 before the integral because you don't need it. You only need the 2 in the numerator. So automatic na siya. So it's a 1/2 ln of the u. You copy everything that you have in the denominator. Okay? Now, number 6. So this is a tangent of x dx integral. If you look at it at first, there's no such thing as an integral of the tangent formula in the trigonometric function. Meaning, you have to write down the tangent into a form which would allow you to integrate it. So what's the equivalent of the tangent in trigonometry? So you know the tangent is sine x over cosine x. Let's say try. If u is set to be cosine x, the du of that is negative sine x dx. So what you need actually in the numerator is just negative 1 or the negative sign. So you will only multiply your original integral by negative 1 over negative 1. You don't need the other negative 1 in the denominator, so it's set before or written before the integral, and you only need the other one in the numerator. So automatic, it's negative ln of the cosine of x, which is your u. Okay? So we're dealing with integrals yielding natural logarithmic functions, meaning integrals after your evaluation is expected to give an answer which is an ln or a natural logarithmic function. So let's go to this seventh example. By the way, wait. You get to see this class. This could still be also, this could be, shall I say, simplified. Okay, let's see. I copy, will copy because there's a need for you to be able to simplify just in case we're in the choices in the that is provided with a particular integral is not the one that you have in your answer. So you may wonder, why is it that my answer is not among the choices? The problem was not that you do not know how to integrate. The problem is it was not simplified. That day you will you will find its equivalent in the choices. So what about this one, negative ln? So let me share to you my whiteboard. It's actually negative ln of the cosine of x. In your differential calculus, whatever is the sign in here, that is the exponent of the argument of the ln, or shall I say whatever is the number that you see here, whether positive or negative, actually that's the exponent of the argument. What do I mean? For example, you see a 2 ln of x. This is equivalent to ln of x squared, or 1/3 ln of y. Actually, this is equivalent to the ln of the cube root of y. Why? Because this one is actually the exponent of the y. Okay, so in this same case, if you'd like to simplify this, this is actually ln of the cosine of x raised to negative 1. What is ln raised to cosine raised to negative 1? That's 1 over cosine of x, right? And what is 1 over cosine of x? That's secant x. So it could be that you don't see this in the answer, in the choices, but rather this one. This and this are equal. So your negative ln of cosine x actually could be simplified to the ln of secant x. Okay? Question? Okay, so let me proceed. So we'll proceed. Now we proceed with this one. So you have ln of cosecant of x. Let's say this is your u, the entire ln. So unique because in this case, you have the u as an ln. So this is your u. The du, the derivative of the cosecant is negative cosecant x cotangent x dx. And it's du over u because it's an ln. We know that the derivative of an ln is du over u, which is this one, cosecant. This is your u, and this is your du in here. If you're going to simplify, this one cancels each other, and what is left is negative cotangent x dx. So the original expression you have in the numerator only needs a negative sign. So you need only a negative sign here and a negative sign outside. So it's a negative of ln of cosecant x plus c. I think this would do. There's no other way of simplifying this. It will only complicate things if we will place the negative 1 here in here as an exponent of your ln of cosecant x. Okay? Now, on the eighth example, you have 1 over the square root of 1, quantity 1 plus square root of x. Again, let's just try. So actually, it's not that you know already that this is just my u. It's just actually a try and error. The more you practice solving, you will see that whenever you see this one at times, if you see something being multiplied in the denominator, you can set one of the two items that were multiplied as your u, not that the entire thing will be u. So in this case, you can set 1 plus square root of x as your u. The du for this, you know that square root of x is x raised to negative 1/2. When we differentiate, the exponent is written before the variable, and the exponent of that variable is subtracted by 1. So this is what is happening here. This is 1/2 x raised to negative 1/2. The derivative of the square root is 1/2. Let me just share it here. Actually, the derivative of your square root of x is the derivative of x raised to 1/2. Rule of differentiation, you copy the exponent and you subtract 1 from the original. So that would be negative 1/2 dx. And this is 1/2, and that one is, sorry, this is 1/2 minus 1. So this is negative 1/2. So negative 1/2 tells you that it's 1 over square root of x dx. There are even problems that simplify this one by multiplying it with square root of x over square root of x, because mathematics tells us that there shouldn't be any square root on the denominator. So the only way that you can get rid of the square root in the denominator is by multiplying it by the square root of x over the square root of x. So your answer actually will be square root of x over 2x dx for the derivative of this one. Okay? But since it's written in this form in here, it's okay. But this one, where it is, this one is also equivalent to this. So let me go back to the slide. So you could see that one in there. So you need a, since you already have the 1 over square root of x here, which you did not include as part of the u in there. So you only need the what, that 1/2. So the 2 should be written before the integral. So it's 2 ln of the u that you have chosen. So the ln of the quantity 1 plus square root of x. Okay? Now, we will proceed. Then we have the natural exponential function. How do we integrate an e raised to u du? This should be interpreted as long as, again, as long as the exponent of your u is together here with it. The derivative of the u is multiplied to the e raised to u. Automatically, your answer is e raised to u. Okay, in this case, you have here e raised to 2x dx. So your u is 2x. The du is 2 dx. You don't have it in here. So what was done is you multiplied by 2 over 2. So you have here a 2 over 2. You only need the 2. So the 1/2 is written before the integral. So it's 1/2, and you just copy the e raised to 2x. Because eu du is just eu. You copy the original exponential function and affix the appropriate constant. In this case, that would be 1/2. Okay. Uh, okay, we go to the next. So that's for e raised to u. We proceed to this one. X squared minus 1, the quantity, multiplied to e raised to x cubed minus 3x plus 1. So let u be this. Since this is your exponential function, so automatically the exponent of this exponential function is your u. The du is 3x squared minus 3. If you factor out the 3, that will leave you x squared minus 1, telling you that you only need the 3 in here. So where you have here, you place the 3 in here because you need it to complete the du, and you place 1/3 outside. It's just like multiplying by 3 over 3. So you have 1/3 here, and you have the 3 quantity x squared minus 1 dx as your complete du. So you just copy. So 1/3, then e, the original exponential expression, e raised to x cubed minus 3x plus 1, plus c. Okay. Any questions so far? Okay, then I will proceed. There were no questions. We proceed with the next. This one, e raised to x square root of 1 minus x. So if you set this as the u, so you have the square root of 1 minus e raised to x. Your du, in this case, is negative e raised to x. Now, remember that this one class has an exponent of 1/2. This one could be written actually as this. Integral of, I'll write it, 1 minus e raised to x raised to 1/2 e raised to x dx. Okay? That's it. Now, if this is your u, this one, that's your u, and this, the derivative of this u is this one, negative e raised to x. Actually, what you lack is just the negative here. So you will multiply by negative 1 over negative 1, just like what's written here. But this will not yield an e raised to u, but rather this time, this will be interpreted, this one, this will be interpreted now as integral of u raised to n du. This is not an integral that will yield an exponential function, but rather an integral that will be using power rule, where n, in this case, your n is 1/2. So look at what happened here. So your 1/2 plus 1 becomes 3/2, and you have 3/2 here. So it's negative integral of this entire thing. So you copy the negative and then you use power rule for this one. Not that your answer will be an exponential function. So negative quantity 1 minus e raised to x raised to 3/2. This 3/2 when written here will be 2/3. So this is now your answer. Your integral did not yield an exponential function but only involved taking the derivative of that particular exponential function. Amo lang na iya ang need niya. The derivative of the u, which is your exponential function. Okay. Any questions so far? Okay, we'll proceed then. Now, number 4. This time we will mix trigonometric function and exponential function. And e raised to tangent of x, secant squared x dx. If you have a very keen eye on functions, you will see right away that this particular tangent, if that is your u, the case that was really the u, will have a derivative which is the secant squared of x. You're seeing here. So then it's already complete. EU du. So EU. So you just copy EU plus C. Because the integral of an EU du is e raised to u. Now, number 5, it's e raised to negative x, the cosine of e raised to negative x dx. This is a classic example, again, of an integral involving an exponential function, but not necessarily that the answer is an exponential function. As you can see, if you set the cosine function, it's like integrating this as cosine of u du class. It's like you're integrating a trigonometric function cosine of u du. If you have cosine of u, for you to have an integral of sine of u, the derivative of the u of the cosine should be complete. In that case, this one. And the derivative is negative e raised to negative x dx. We know the derivative of an EU is EU du, the du of the negative x, which is negative dx. So you just need a negative sign. So you need a negative 1 over negative 1 here, and that's the negative 1 that you're seeing here. So negative integral of, this is your, This is your cosine u, and this is your, ini sila. This is your du. So your answer is negative. The integral of the cosine is sine of e raised to x. The negative here is not the integral of the cosine, ha? But the negative came from the negative 1 over negative 1 that you needed. That way, the u of your cosine would be complete in here with the negative 1, negative e raised to negative x. So the fifth example does not yield an exponential function, but rather deals with an exponential function. It's just a case of a trigonometric function that was integrated. Okay? Any question? None? So let me erase this because this will appear in my next slide. Okay, we go to the next. Now, uh, the second topic was integrals dealing with exponential functions and integrals yielding with exponential function, and that's the e raised to u. This time, we are going to talk about the integral of an exponential function, but it's a one wherein you have a base which is a constant. It's not an exponential function na eu, but rather what you have here, this a is a constant. It's a constant. And I'll change the color. And this one is your variable. This is where the variable is. A is a constant and your u is the variable. Whenever you have a base constant and a variable exponent integrated, what is important, class, is you check whether the derivative of your variable exponent is complete in here. If it's complete, then what you will have is a case of 1 over ln A. This is a constant because A is a constant. Then you copy also AU. It's just like EU, which you copied also. But the thing is, you need to introduce a 1 over ln A because this base is a constant, not an exponential function, a natural exponential function, the E. Now, take for example this one. So if this is your A and this is your variable, okay? So automatically, you just check the derivative of this U, and that would be 2x dx. What you have here is just x dx. So you need to place a 2, and you need to place here 1/2. So equivalent to multiplying by 2 over 2. Now, your written integral, if we will rewrite the original integral, that would be 5x squared or 5 raised to x squared times 2x dx. I'd like to rewrite this in a manner that you will understand the integral of 5 raised to x squared times 2x dx. Now, what you have here, this is your a raised to u, and this is your du. The derivative of your u in here. Now you place a 2 in here, so there must be a 2 outside, or rather 1/2, because it should be 1 always that you will multiply to your integral. So 1/2 times 2 is 1. Then your answer will be an ln, or 1 over ln of 5, the base, just like here, 1 over ln of 5, and you affix the 1/2 before that you have written before your integral. So that would be 1 over 2 ln of 5, and you just copy. You copy the AU. This one is your 1/2 ln of A being 5 in this case. Okay? So this is the integral of a general exponential function. If I'm going to call it, it's an exponential function in which the base is a constant and the exponent is a variable. Comparable gid ang integral nila sa e raised to u. Only that you have added this constant here, which is 1 over ln of a. But the approach is you are allowed to write a raised to u, or you are allowed to copy the original exponential expression with a constant base as long as the derivative of its exponent is complete here. You're allowed to do that. It's the same principle that we are using in a natural exponential function. Okay? So that's for your exponential function in which the base is a constant and the exponent is a variable. Any question? Any question? Okay, none. Sige, we'll proceed. Then we go to the second. 3 cosine of x, sine of x dx. Automatic, you could see that I have a constant base here. So this should be my a raised to u. And if my u is cosine of x, the derivative is negative sine of x dx. In that case, and the a is 3. So that's your base. In that case, then you need the negative sign for the derivative here. So there's a need for the negative 1 over 1. So it's negative integral of 3 cosine x. This one is the derivative of the u. So what's the answer? You copy the original a raised to u. This is it. And then you just affix the appropriate constant. So the negative 1 there, don't forget. So negative 1 over, per formula, it should be 1 over ln of a, which is 3. So 1 over ln of 3. I just have negative because of this negative sign here. Okay? For an exponential function with a base, which is a constant. Okay, it's easy, class, because we're doing this topical. So you would know, okay, Miss Ali is talking about exponential functions. So I'm expected to process everything using an exponential formula. It's a different thing when everything is already given to you and you are to think what particular formula you will use. So why am I telling you this? Because there's a need for you to practice integrating. Now we go to the third. So it's 3 ln of x squared. So now you have here married. There's a mix of principles here. There's an exponential function which is having a constant base. The exponent is an ln function, which of course you know how to differentiate. So let's see. Now, you have 3 ln of x squared over x. If you set your u to be ln of x squared, because this 3 here is a raised to u, then your u is ln of x squared. The derivative of ln of u is du over u. Du over u for the ln of u. So this is the du. The u of your ln is x squared. The du of that is 2x dx. The derivative of ln u is du over u. So this is the x squared. Okay? Now, if you would simplify, this would require a 2 over x dx. Now, it just so happened that you already have a dx over x. So what you need is just the 2. So you need to multiply by 2 over 2. And what you don't need for as part of your derivative, you place before the integral. So it's a 1/2. And this is your 2x or 2 over x dx. That would be your complete du. And this is your au. So what would be the answer? Copy the au and then provide the 1 over ln of a, which is 3, and then copy the 1/2 which you have set aside. So it's 1 over 2 ln of 3, 3 ln of x squared plus c. So you have married actually the logarithmic function here, derivative, and the integral of an exponential function with a constant base. Let me see, class, because I need to admit somebody. Wait, class, Okay, wait. Why is it gone? It's gone. Okay, any questions so far? None? So we will proceed. This one. Hmm. Okay, x plus 1, quantity e raised to x, 6x e raised to x dx. Now, if you look at it, you have to, when you process an integral, class, you look for the complicated expression and make that as your main function. And then determine in your main function what is your u. If you look at this, the most complicated expression is 6x e raised to x, right? So you have to make this as your main function, meaning this should be your main u. The others might just be your derivative of the u. So what do you mean by that, miss? So if you set 6 raised to x e raised to x here as your u, the derivative of this is derivative of a product. Why? Because you have multiplied x with e raised to x. So when you process this, first term times the derivative of the second plus the second term times the derivative of the first, which is 1. You've learned this in your EMA 101. So product rule. You use product rule of differentiation. Copy the first term, multiply it with the derivative of the second, plus copy the second term, multiply it to the derivative of the first, which is 1. So this is actually your complete derivative. So see, if you factor out the e raised to x, it needs to be multiplied to x plus 1 for it to be same as this one. And looking at what you are provided in your integral, since you already set this as your u, the main function, which is a raised to u, everything here is your du. So then, you copy everything here. So since this is your au, you copy 6 rather raised to x e raised to x times 1 over ln of a. So 1 over ln of 6. And that's it. You, at first, you will look overwhelmed. It's overwhelming because if you're not really practicing, what is this? There's so many things being multiplied here. But as a rule, when I was a student, I tried to look for the most complicated expression in my integral. If there are several that I could see, several functions that I could see, and I try to make it as my main function. So in this case, this is the most complicated. Maybe, just maybe, the remaining terms will be my derivative for my main function, which in this case really agreed with our assumption na the remaining expression is really the derivative of the main complicated expression. Any questions so far with the exponential function? None? Okay, so in 10 minutes we'll be done. So let me check if we will be having more examples on this. If not, we will... okay, so that would be for to now. So on Wednesday, for now rather, for today we've learned how to evaluate. So review ta. We have learned how to evaluate expressions yielding natural logarithmic functions. We have learned how to evaluate expressions yielding exponential functions. And we've learned how to evaluate integrals having exponential functions. Then the third is we've learned how to evaluate integrals yielding exponential functions with base that are constants. And that's the one that we're solving now. And we have learned that very important learning is that I've shared with you is whenever you're given a complicated expression to evaluate, please try to select the most complicated function or expression and set that as your u, your main function. Probably, just probably, the remaining expression is your du. Sometimes they just need a constant to complete them, or they need just a sign to complete them. Okay? Now, since we did not have any class last week, this Wednesday, I will still meet you to cover for the time that I was not able to have synchronous meeting with you. So we will continue with techniques of integration. On Wednesday, we will have your next quiz the week after that would be next week. Now will be your second quiz. That way you will have a lot of time to do your practice. Anyway, Friday is your me time, so it depends on you if you're going to do that or use that in practicing solving. Okay, so for now, class, I will stop sharing. Do you have any question for now? Oo, nalimtan ko gid Kent mag-record. Thank you. You have any question? So I will be sending you a new link in our GC for Wednesday's class. We will meet on Wednesday. I think the dean was able to explain the essence of having to meet not just once a week. We might be meeting twice a week to cover for topics that we haven't covered because probably your teacher was sick or I need to attend a meeting. And in my case, I really need to attend some meetings most of the time because I'm also handling office. I'm also handling administrative work. Okay? So I'll be hearing from you again on Wednesday if there aren't any more questions. No more questions, class? Okay. Okay, then bye for now. I will hear from you again on Wednesday. Thank you, class.
Thank you, Miss.
Okay, thank you.
Bye, Miss. Thank you.
Bye-bye.